Good morning, afternoon, and evening. I'm C. Nataraj, the Moritz Professor of Engineered Systems at Villanova University in New Philadelphia. I direct an interdisciplinary research center at Villanova called VCATS, or Villanova Center for Analytics of Dynamic Systems, which is hosting the symposium in collaboration with the Franklin Institute. Most people who visit Philadelphia know Franklin Institute as an engaging and fascinating science museum, but it's also the institute that manages and sponsors the Benjamin Franklin Awards, which have quite a history, as we will learn. Understand that there are more than 220, 230 attendees from all around the world. It's indeed my pleasure to welcome you to this unique symposium. This symposium coincides with the awards week at the Franklin Institute, and today we are honoring Professor Dan Mote, who is the 2021 Benjamin Franklin Awardee in Mechanical Engineering. I'm honored to chair this symposium as a representative of the Committee of the Science and the Arts at the Franklin Institute, which is generally acknowledged to be among the oldest scientific awards committees in the world. First, we're going to kick off with a video about Franklin Awards, which is a far more interesting way to learn about this than listening to me. Dan, you want to play the awards video that says Declaration of Progress?
In the course of human events, a spark of inspiration sets the world ablaze with the fires of enlightenment and puts us firmly afoot on the way of progress, connecting us to one another in ways that elevate all of humankind to equal stations in which to pursue understanding. A decent respect for innovation requires that we recognize those who so affect our receding horizons, using only that to which the laws of nature entitle them, and declare that these inspired few are the architects of our future, and their insights the foundation upon which humankind distinguishes itself from all others. And with this, we hold that truth is not always self-evident, that it sometimes lies deep below the surface, and that the deserving are those who dare to seek it there, and then return to spread the word and say that with a single moment of inspiration, we have truly moved forward. This is our Declaration of Progress, a legacy spanning nearly 2 centuries. The Franklin Institute Awards, the spirit of independence, emanates from Philadelphia.
Well, I hope that was interesting and inspiring to learn about the legacy of the Franklin Awards. I mean, it's 1824, I think, when they started. Uh, Next, we have Dr. Daryl Williams, Senior Vice President of Science and Education at the Franklin Institute. He's going to say a few words about today's symposium. Dan, could you play the video?
Just 1 minute, please.
Yeah, take your time. The one that says Mote Zoom DN.
Good morning. I'm Dr. Darrell Williams, Senior Vice President of Science and Education at the Franklin Institute. It is my pleasure to welcome you on behalf of the Institute to this special program honoring Dan Mote, recipient of the 2021 Benjamin Franklin Medal in Mechanical Engineering. We are proud to induct Dr. Mote into the legacy of the Franklin Institute Awards. Since 1824, we have honored more than 2,000 scientists, engineers, inventors, and entrepreneurs for the most groundbreaking achievements of the past 2 centuries. Our laureates have truly changed the world with their remarkable work, and Dr. Mote is no exception. Typically, every spring, our newest class of laureates gathers in Philadelphia to participate in a week-long celebration of their achievements. During this time, they engage learners of all ages and levels in a broad range of educational experiences that best represents the Institute's mission to inspire passion for learning about science and technology. But as you know, this isn't a typical year. This year, we have the opportunity to engage even more people by hosting our programming online, including today's symposium. I'd like to thank Villanova University and the Villanova Center for Analytics of Dynamic Systems for hosting us today. Villanova has been a wonderful lifetime partner of the Franklin Institute in so many exciting initiatives, and we are grateful to them for making this symposium possible. I would also especially like to thank Nataraj for all of his work organizing today's program. We owe Dr. Mote's presence today to Dr. Nataraj. He is Dr. Mote's laureate sponsor, the member of the Franklin Institute's Committee on Science and the Arts, who along with other members of the Civil and Mechanical Engineering Subcommittee, led the investigation of Dr. Mote's work, a process that can often take years. Dr. Nataraj was tasked with convincing the full committee that Dr. Mote's work was worthy of this recognition. And as you can see, he was successful. Thank you, Nat. Dr. Mote's award, along with 6 other Benjamin Franklin medals, the Bauer Awards for Achievement in Science for Leadership Development, and the brand new Benjamin Franklin Next Gen Award will be presented during our virtual award ceremonies this Thursday, April 29th at 7 p.m. Eastern Time. Details on how you can view the ceremony are on our website, www.fi.edu. I hope you will join us then. On behalf of the Franklin Institute, congratulations to Dr. Mote, and thank you for joining us today.
Thank you, Daryl. Really appreciate your words very much, especially about me. Wasn't expecting that. Folks, I'd like to take this opportunity to welcome you all again, albeit virtually, to Villanova University. If and when the COVID curse lifts, I would like to invite you to come to a beautiful and welcoming campus in suburban Philadelphia. With that, I would like to introduce Dr. Michelle Marcolongo, Drostic Dean of Engineering at Villanova. Michelle has I'm not doing her justice here with this brief intro, I should say. Michelle has an outstanding career as a teacher, a prolific researcher, entrepreneur, and administrator. And we're indeed fortunate that she chose to come to Villanova University as our dean. Michelle, go ahead. Thank you.
Thank you. And a professor of mechanical engineering, so I can appreciate all of the accomplishments and discussions that we'll be having here today. Thank you so much, Nat, for your time in bringing this renowned group together. I think we're in for a wonderful and very interesting session. And Dan, again, let me congratulate you on your Franklin Medal, so well deserved. Growing up around Philadelphia, I learned so much about Ben Franklin. I read his books and toured his house on Market Street. While remembered for his essential statesmanship and the founding of our country, Franklin was truly a Renaissance citizen of the world. As an engineer, I've always appreciated his ability to define a challenge and to come up with a solution, especially his technical contributions. For example, when sawmills became efficient in Philadelphia and people started building wood-framed houses, tremendous fires became commonplace in the city. In response, Franklin recommended structural modifications to make houses more fire resistant. He invented the lightning rod and developed the first volunteer fire company in the nation, with firefighters trained in the science of firefighting. Truly a holistic and society-focused engineering solution. In many ways, Ben Franklin modeled today's engineers who use our creativity and technical knowledge to advance the state of society. whether through adding safety features to existing designs like Ben, or coming up with completely new solutions to help humanity. While our work has transformed the world in countless ways, we as engineers are generally humble souls who can finish one project and then start on a new challenge the very next day, often without stopping to tell the story of what we've accomplished. Consider, for example, that we just flew a helicopter on Mars, signaling that exploration and the potential settlement of this little known planet is possible. Have we considered the enormity of this single transformational feat? Instead of sharing the implications of this accomplishment widely and as loudly as possible, we engineers tend to be more concerned with the blade aspect ratio, materials used to make the copter, appropriate blade speed for the atmosphere on Mars, and the control systems. These are the nuances that matter to us, of course. But the impact of our work on society should also be taken into consideration. And society needs, likewise, to recognize the role of engineers in forging this new future. So where millions of Americans can likely name the actor in the 2015 movie The Martian, it was Matt Damon, how many can name the chief engineer on the Mars Ingenuity helicopter? Can you? It was Ms. Mimi Ong. In his 1996 book, The Existential Pleasure of Engineering, Samuel Florman discusses the link between engineering and society from an ethical, moral, and unintended consequence perspective. He argues that a liberal arts component in engineering education may help engineers think through the consequences of their work, both the good and potentially harmful. When I was a student, I always dreaded liberal arts courses, especially where writing papers was involved. And I can still miss a whole column of Greek mythology questions on Jeopardy. However, when I took my only course in philosophy, I found myself intrigued. Now, when I listen to podcasts and read books, they're often about psychology, history, philosophy, and other topics that I didn't appreciate in my undergraduate engineering days. But I believe this self-guided education has made me a more well-rounded engineer and has allowed me to ask the right questions before developing an engineering solution. The breadth of thinking does bring challenges when considering engineering curricula, as I do with my colleagues at Villanova University. Here, we've developed an approach to engineering that is rigorous, but rooted in liberal arts education. I give the engineering students a lot of credit because the liberal arts students are not rooted in an engineering education. But I know our engineering students benefit from the exposure of different ways of thinking and grow to appreciate different schools of thought. We balance this education with a learn by doing approach in our engineering curriculum, where students start the first year with design, have professional development courses every year, do humanitarian engineering service trips globally, work with our world-class faculty in their research labs, and generally do what engineers love to do in our maker spaces. This powerful combination educates technically proficient engineers who can also be leaders in society, and we have seen our Villanova alums do just that. So we are delighted that you could join us today in honoring Dan Mote. And again, welcome all of the speakers and attendees virtually to Villanova University. Thank you.
Thank you, Michelle, for an awesome welcome. And as you were talking about Ben Franklin, I was just thinking, Ben Franklin is credited with inventing bifocals, although there's some argument about that. I was thinking, what would I do without bifocals as I get older? An amazing guy, no question. Okay, folks, now it's time to get on, get serious and get on with the symposium. So just maybe I'll speak 3-4 minutes about how the genesis of this. So the Benjamin Franklin awardee, Professor Mote, and I discussed the symposium topics. And rather than having about sort of surrounding the areas of vibration, which is what Professor Mote is getting the award for, we discussed that we felt strongly that it should be a larger picture of why engineering is the most critical influencer for humanity. When Dan mentioned this, I completely synced with this, that we should really about the larger picture and, why engineering is the most important thing probably for society in the 21st century. Um, and really, no question that humanity has achieved tremendous progress during the 20th century, the last century, in large part due to advancements in engineering, although it's often not acknowledged. But rather than dwell on the past, we thought the symposium should explore how the changes in society will be surpassed and perhaps even dwarfed by the advancement that we will see in the 21st century. We have a very distinguished panel with Professor Dan Mote, Vijay Kumar, Rashid Bashir, and Arun Majumdar. They will have short 20-minute presentations, following which we will have a simulating discussion on the immeasurable impact engineering can be expected to have on society. In it's really difficult to predict, right? There is a famous prediction by IBM CEO from the 1950s, I think, where he said the computing has reached its zenith. This is it. It's not going to get any better, or something like that from IBM, right? So we won't hold any of you to this, although this will be recorded for posterity. I should mention that in passing. But I think it's good to speculate anyhow. And clearly, we could talk about these and other topics for days, but the constraint to have the symposium in 3 hours unfortunately limits the topics. But I think we picked the most important ones, namely automation, autonomous systems, energy, environment, and materials within that, bioengineering, and medicine. And we could not have picked better experts than we have on this panel. I'm really excited and honored to be moderating this unique event. Just a few logistical items before we begin. We will have individual presentations by the panelists, which we plan to wrap up by around 10:45. We will then take a 10-minute break and follow up with an open discussion period for an hour. Please, to the audience, please feel free to type your questions in the Q&A box, and we will get to as many as we can in the time we have. I should also tell you that we are recording the event, and it will be edited and curated and distributed on Villanova University's YouTube channel. And the link will be emailed to you, to all the registered attendees, once the video is ready. Okay, on with the show. Our first speaker will be the laureate, Dr. C. Daniel Mote Jr. Professor Dan Mote is the Regents Professor and Glenn L. Martin Institute Professor of Engineering and former President of the University of Maryland, College Park. He's also the President Emeritus of National Academy of Engineering. He's a recipient of numerous awards and honors, too many to mention in the short time I have, so I'll mention just a few. Dr. Mote is a member of the National Academy of Engineering and the American Academy of Arts and Sciences. He's won the ASME medal, what we were just talking about earlier, its most distinguished recognition, and is a fellow of the International Academy of Wood Science, the Acoustical Society of America, and the American Association for the Advancement of Science. Dr. Mote received BS, MS, and PhD in mechanical engineering from University of California, Berkeley, and then decided to move away from the West Coast. If you also watch the award ceremony on Thursday evening, which by the way is virtual and free this year, it's always been a big ticketed item or on invitation only, and probably will be again in the future. So here's your chance to watch it for free. But there will be a very nice introduction to Professor Mote, so please watch it if you can on Thursday evening. We'll put the link in maybe in the email that you get it. Okay, Dan, I think it's all yours. You have about 20 minutes.
Oh, okay, Nat. Thank you very much. And I thank very much the entire panel for putting up with me. And I consider this a great opportunity to actually talk about things I like, and that's basically the future of engineering. So I'll be kind of direct in my comments, and I'm not apologizing for it. I'm just warning you about it. So at its close, the 20th century was seen by many people as the century of engineering. In fact, that inspired 27 professional societies in the US in 2003 to rank the 20 most important engineering contributions of the 20th century. The National Academy actually published a volume titled A Century of Innovation, 20 Engineering Achievements That Transformed Our Lives. Almost immediately, questions were raised about the 21st century. What about engineering in the 21st century? So in about 2007, the NE appointed a very distinguished international committee of 18 experts to predict the greatest engineering achievements would be happening in the 21st century. Bill Perry, the former Secretary of Defense, Stanford faculty member, very distinguished person, along with 18 others, including Nobel laureates and Dean Kamen, and so on. It's really a great committee, and they were from some Singapore and Asia and Africa and Britain and so forth. They're all over the place. The committee got together and it immediately said, it's impossible to answer this question. They don't even know what areas of engineering are going to be important, let alone picking the most important one. But it offered an alternative. It offered to predict what engineering needs to achieve in the 21st century based on current understandings. And it could do that. So that was acceptable, of course, when this committee says that's what they want to do. And that led actually to the Grand Challenges for Engineering and the Grand Challenge Scholars Program. And I'll return to this topic in a moment. But basically, there was no sense at the time that the 21st century was going to be the most important century of engineering at that time. Now, after 2 decades, it's clear that the 21st century will be the century of engineering, as a matter of fact, in my view. No question about it. It's the greatest and fastest transformation of engineering in history right now. The country has not caught up with this yet, by the way. The country speaks about advancing technology instead of engineering, which of course always drives me crazy. I will concentrate on the 21st century look of engineering after we comment on what engineering is actually about. Might as well start there. To learn the essence of science or the essence of engineering, we can undertake a Google search basically on those questions to get the kind of public's answer to that question. If you look at the essence of science, doing this, I did this in fact, it's very clear and very straightforward. It's about discovery and understanding of fundamental phenomena. And that's what science is about. And the scientific method, in fact, is the accepted process for validation of the understanding of the discovery. Now, if you do the same thing for engineering, what you find out is the following points. I'll just tell you what they are, trying not to comment on them individually. One, you have to learn by doing things. That is the essence of engineering. That's the statement. Understand the important role engineers play, spending decades pursuing ideas through trial and error. That's another essence of engineering. Engineering is the application of science and math to solve problems, if you believe that. Engineers find practical uses for scientific discoveries. So we're kind of a subset under science. We help science. Engineers apply science and math to develop economical solutions to technical problems. A good engineer makes design work with as few original ideas as possible. That's another one. Engineers use models provided by science to solve problems that benefit humanity. Okay, none of these are even close to true and have never been so, as a matter of fact. And that's the problem we've got is even the experts who are projecting that they know about the essence of engineering actually don't know squat about it, as a matter of fact. No wonder the public is so confused about what engineering is, because basic information is not there. Engineering is not a supplicant to science. It's not even part of science, in fact, at all. While scientific understanding is often helpful, of course, it is not conditional constraint on engineering. Egyptians built pyramids about 4,000 years ago without science. Polynesians navigated the oceans about 2,000 years ago without science. In fact, they're both practiced engineering without naming it so, by the way. The essence of engineering was first named and established by the Romans 2,500 years ago, when they named the first engineering field after its most important users. That's what they did. That was military engineering. Roman legions used superior military creations for its renowned military capabilities, and they were feared and trusted both, depending on which side of the problem you're on. Rome initiated the practice of naming fields of engineering after the users of the creations. That's what the Romans did. And creations for users is the engineering practice that continues to this day, as a matter of fact. That, I believe, is the essence of engineering. Time does not permit us to do a complete justice to this issue. Suffice it to show the stark difference between science and engineering, and that they are not commingled at any level. Allow me to step forward from here. Engineering's essence is to create for users, and it has served humanity, prehistoric humanity, and in fact, other life forms too, such as insects, fish, birds, and mammals unwaveringly for millions of years. Creation for users is not limited to human users, as a matter of fact. Other life forms pass down engineering capabilities, most likely learned from their predecessors, such as creating anthills, creating beehives, creating birds' nests, among many, many others. These creations are likely not original creations for each opportunity. The response of these creatures to disruption of their circumstance, like stepping on an anthill, demonstrates that the inhabitants there are fully prepared to respond. However, these life forms also learn by observation as well. For example, horses learn how to open gates of their enclosures by observation. What distinguishes human engineering from engineering of all other life forms is the singular human capacity to envision a creation that is needed, then to create it, and ultimately to implement it, fulfilling a user need. That's what distinguishes engineering from maybe millions of other practices of engineering throughout the life forms on the planet. Without new creations, user advancements are limited. Only human engineering leads to significant new creations, with the result being remarkably significant new user advancements that are commonplace today. Modern humanity is 300,000 years old. Languages date from 50,000 years ago, and Homo sapiens were chipping sharp tools from stones about 3.5 million years ago, as a matter of fact. At that time, humankind was not the preeminent life form on Earth. Humans' dominance evolved through the incessant human process of creation for users, with new thoughts and capabilities that an advanced user needs for life, knowledge, and prosperity. Other life forms could not advance as humans did because their limited capacity to adapt to their needs for action and development, and their inability to deduce new creations on the spot. It is a long, dominant human engineering story that has led us to today's advanced standing of the human species among all other life forms, and not to extinction. Consequently, over the millennia bringing us to today, we can now ask whether human engineering should use its dominant global position in the 21st century to preserve the planet rather than to exploit it. This is an important, apparently rarely addressed, new question for engineering. Let us return now, after this introduction to what is engineering, to the Perry Committee and Bill Perry and how it deduced basically what engineering needs to achieve in the 21st century. The committee approached the question as an engineering system problem, basically. Engineering system problem is composed of three fundamental elements. There's vision, there's goals, the objectives. The vision characterizes the destination of the solution. There is a vision statement, a short but specific destination. A non-technical part of the solution, basically serving the general user, it expresses the user benefits and needs. Everything in the engineering system problem follows the vision statement and presents all the technical problems. The vision statement controls problem solution. The goals, then, are the engineering system problems that are required to satisfy the vision statement. Technical solutions required by a vision statement are the goals, And the number of goals also depends on the vision statement, because the number of goals has to satisfy all the statements in the vision. The objectives then are engineering system solutions required to satisfy each goal. So the vision statement for the Perry Committee problem was basically 15 words long, and it lays out the entire problem in 15 words. And those 15 words are continuation of life on the planet, making our world more sustainable, secure, healthy, and joyful. So the goals include all the engineering system problems whose solutions will deliver the vision. Now, if you look at this, at that statement, it's talking about continuation of life on the planet. It doesn't talk only about human life, by the way. The implication might be to some, but it's basically life on the planet. It's not going to expire, in other words. Making our world, that is the entire world, more sustainable, more secure, more healthy, and more joyful. That's quality of life, if you like. So that's the statement. That's the vision statement, basically, for the grand challenges. And then the goals are selected to deliver all those elements, and that's where the goals come from. And you want the minimum number of goals, so you have the minimum number of problems you have to solve in order to get there. But that's every goal is essentially looking at that vision statement before it decides to do anything. And it turns out that the Perry Committee found 14 goals that are necessary for this. And I don't want to talk a lot about these goals because they're fun to talk about, by the way, but we don't have time for it. But there are things like make solar energy economical, advanced health informatics, advanced personalized learning, enhanced virtual reality, manage the nitrogen cycle, and things like that. Big topics. But the 14 of them. I'll give you an example of how this might work. The vision statement talks about continuation of life on the planet, making our world more sustainable, secure, healthy, and joyful. So let's look at healthy, just for example. Look at healthy. So we look at the goals. Okay, there are a number of goals. One goal is advanced health informatics. Another goal is reverse engineer the brain. Another goal is engineer better medicines. And there's another goal that says provide access to clean water. And another goal is restore and improve urban infrastructure. And even there's one that says enhance virtual reality. So you might say all those goals I just read off to you would deal with health issues one way or another. So that's why healthy is being covered. So there isn't a particular goal that says do something healthy. No, it's all the pieces would make that up. And that would be true for sustainability, for security, and quality of life as well. So the 14 goals, by the way, are termed the grand challenges for engineering as well, which just really it disguises the vision, which is a big mistake, because the vision is really what the problem is about. The goals are just are to deliver the vision. That's why they exist. So you have a number of people these days, for example, that want to drop goals. I don't like this one. I'd rather have another one, and so forth. Well, you can't do that without changing the vision statement. And of course, the vision statement is where you're going. So therefore, as the destination, you don't want to drop the goals. Now, the objectives, they provide the engineering system solution to each of the 14 goals. And so, so you need to have the solution for each of these 14 goals. And there are really two possibilities to look at this solution. I think they're both worth mentioning. There's one possibility: you have an initiative group. You might think of it as a kind of, I don't know, a company that has tremendous expertise. The initiative group basically has all the talents needed for the problem solution. You give them the problem, they can solve the problem. There's no uncertainty here. That would be the initiative group. On the other hand, there's another group called the talent. We call it the talent group. The talent group. The talent group has the capabilities to address the problems, but without proven talents to do so at the moment. That's the talent group. So those are the two groups. that will take on the objectives. The initiative group creates the solutions to the goals. The talent groups creates the workforce to address the goals. Engineering students, for example, they'll populate the talent group to start with. It's the Grand Challenge Scholarship Program that prepares this talent group of students for the subsequent initiative group that they will play as well. So if we look at what the outcome has been of this process, the Grand Challenge Scholarship Program that at universities, now I only have the date from 2019 at the moment, but at that time, there were 75 universities in the United States that had the Grand Challenge Scholarship Program, plus another 83 in the United States that were expressed interest in expanding the program as well. And that's quite a substantial number. If you think of the 250 or so engineering fields that are significant in the country. There are 17 international universities that had the Grand Challenge Scholarship Program, and another 53 of them exploring the program as well. So you can see the program was very interesting to students. And in fact, many of these programs were created by the students. The students got together, they decided they want to do this. They got a faculty member who was willing to listen to them, and then they went to the dean and pressed the dean to start a program. Let's get on with it, sort of thing. Yeah. So the students expressed interest because they see the topic as the current direction of the engineering world, and accordingly their future. They had some other important points for these students as well. They recognize culture and economic considerations are often critical to the viability of engineering solutions. These are now the students of the 21st century students. These are not students from the 20th century. They realize that multidisciplinary and multicultural engineering teams undertaking complex system solutions are often transformative. They're thinking big already. And they understand that the vision of engineering solution is controlling the solution. So with vision, goals, and objectives, the grand challenges for engineering then can be addressed. So a couple of concluding remarks here. With today's expansion of the field of engineering is accelerating in both the subfields and the activities. It's substantially increased attention to people in society. Attention to people in society did not exist in the 20th century engineering and earlier. In fact, many people went into engineering, so they didn't have to deal with people in society when I was a student, as a matter of fact. Engineering has moved into responsibilities that are no longer the singular responsibility of government and has even surpassed government, such as in capturing intact rocket parts on floating platforms in the ocean. It's in space as well. The space shuttle now is a private enterprise that serves a space station. Interplanetary travel also has strong private interest and activity as well, even developing places to land and partner and live on Mars as a private sector. Medicines, medical practice, robotics, imaging are all private and expanding in many different directions. Engineering is expanding its innovation space substantially by establishing higher level of corporate responsibilities with, for example, there are $4 trillion engineering enterprises now, Apple, Microsoft, Amazon, Alphabet. They are in an entire layer higher than engineering was in the 20th century, not even in the same planet, shall we say. These four are the nation's only trillion-dollar companies, by the way. At this scale, engineering needs to be broader, more encompassing, and possessed of multidisciplinary, multicultural reach and talents. National power of engineering has increased remarkably in 2 decades alone, and its leadership projects that this power is neither a fluke nor a short-term substance.
2 more minutes, Dr. Mote.
This major leadership layer did not exist at all 20 years ago. It expands engineering's view of itself and its opportunities across the spectrum of national needs. Opportunities for engineering students are very strong, exciting, highly multidisciplinary, and multicultural too. Students in the 21st century embraced responsibilities serving people in society, which of course was the opposite to the 20th century. Engineering then was a field chosen to avoid dealing with people in society, as I've said. The nation as a whole has not recognized this as an engineering transformation quite yet, as it tries to avoid using the E word at all, if at all possible. It continues to substitute the word technology for engineering, a correctable error awaiting attention. Now, I hope that you understand why I say the 21st century is the century of engineering. For the younger people in our audience, this is your time, your future, your adventure. So go for it. Thank you very much for your most polite attention.
Thanks, Dan. It was awesome and right on time as well. Some very surprising insights. Um, I'm sure it'll get a lot of questions from the audience. And I wanted to say, I know, I followed your Grand Challenge program, and I was one of those primarily responsible for bringing it to Villanova because became a big fan. I'm really a big fan of that program.
Thank you very much for that.
And folks, a reminder to type away your questions, and we'll get to them in the Q&A session at the end, rather than break this up. Next, we have Professor Vijay Kumar. Again, a very brief bio. Dr. Vijay Kumar is the Nemirovsky Family Dean of Penn Engineering, with appointments in departments of Mechanical Engineering, Applied Mechanics, Computer Information Science, Electrical and Systems Engineering at University of Pennsylvania. He received BTech from IIT Kanpur and PhD from Ohio State in '87. He's been on the Mechanical Engineering faculty at Penn since then. He has served as Assistant Director of Robotics and Cyber-Physical Systems at the White House Office of Science and Technology Policy. His lab has spun off many startups in robotics. He's a founder of Extend Technologies. He's a fellow. Dr. Kumar is a fellow of ASME and IEEE. He was elected to the National Academy of Engineering in 2013 and the American Philosophical Society in 2018. So we may look forward to some philosophical insights in his presentation next. Vijay?
Thank you, Nat, for that wonderful introduction, and thanks to you and Dean Marcolongo for hosting this. It's an honor to speak at any of the Franklin Institute ceremonies, but particularly an honor to speak, to share the same Zoom screen, if I might, with Dr. Mote. Dan, I've always looked at your words and they've inspired me over the years, particularly now as Dean. And I'd like to say there are two things that I take with me when I go talk to students, to talk to my fellow deans. One, of course, I'm at Penn, and of course, this is about Franklin. And I'd like to say that Benjamin Franklin always looks over my shoulders. And indeed, this is not a virtual background. There is a bust of Benjamin Franklin right over my shoulders. But the other thing is I'm always reminded of, so in 2013, I heard Dan talk to the National Academy of Engineering. And in that speech, Dan, I don't know if you remember this, you talked about lighting 3 fires and starting 3 initiatives. And I'll tell you what those fires are, but I'm just reminded a full 8 years later, those are the same 3 fires that I continue to light. And the first fire is, of course, important of talent in the engineering workforce. The second fire is that engineering is not a national thing. It's an international thing. There's a global role that engineers play that has to be understood, that has to be emphasized. And the third, I think Dan said it much more eloquently than I can, which is really about the visibility, the understanding of engineering, and telling the general public what engineering is all about. And these are familiar issues even today. And as Dean of Engineering, we have a relatively small engineering student body, but today engineering is not just for engineering students alone. I truly think that engineering is a liberal art, and it's our role as engineers to take it to the rest of the campus, if you will. And that's something I've taken to heart in my deanship. I have a few slides in the remaining 18 minutes or so. I thought I would touch upon the things that, that Nat asked me to talk about. So I'm going to share my slides. Hopefully this is not a big challenge. Just give me a second. So hopefully you can see the slides. So what I thought I would do is tell you a little bit about some of the work that I do with my students in my lab, just to give you some context of where I'm coming from when I approach this subject of autonomy. And we primarily work on autonomous flight. But going back to Dan's opening comments, I think one of the most exciting technologies is really the automation that we see in self-driving cars. And I want to say a little bit about that and where that field is headed. And then finally, and I do appreciate the sensitivity of using the word technology versus engineering, but AI is thought of as a technology. So to me, there's a fundamental science, a fundamental engineering spirit behind it. It's about creating new artifacts, creating new devices, because it's embedded now in our physical world. And it's an enabler of automation. And I put a question mark to it because I want to speculate at this point. And then finally, I also want to speculate about the impact on society, especially as we go into, we're well into the 21st century. So what impact will these technologies have? So just a little bit about myself. So we work on autonomous flight. And again, going back to the engineering grand challenges, most of our work addresses two aspects of sustainability. We work on the forestry problem of forestry. So just to set things in context, 30% plus of our world's land is covered with forests, and yet we don't know the amount of carbon that exists in the forest. Yes, we have estimates, but they're very crude. The best way to measure how much carbon you have is by doing spot checks that human beings, spotters, go around and actually measure diameters of trees in timber forests. The other one is precision agriculture, where we work on trying to monitor the states of plants, crops. So much of our work is about monitoring and mapping. We'd love to be able to tell you how many forests, how many trees are there in Wharton State Forest, which is very close by, how many apples are growing in the Biglerville orchards near Harrisburg, Pennsylvania. And the farmers today don't know that, neither do the folks who actually cultivate the forests. So I want to show you a video. Let me turn down this, which explains a little bit about how our UAVs work. So we work in GPS denied environments. There's no infrastructure. It's a completely unstructured environment. And what you see on the screen on the top left is what the UAV sees. What you see in the bottom left is what the UAV actually thinks of as relevant information as it navigates this unknown territory. And what you see on the right side is an asterisk, which denotes the goal, where we're asked to go and locate interesting objects. It could be apples, it could be trees. This happened to be a DARPA project, so it happens to be a red barrel. It doesn't know about the existence of the building. And it's constantly trying to find its way to the rough location of where this red star is. It does not have GPS, so all the while it's dead reckoning, this idea that you count the number of steps and you try to estimate where you might be. But of course it has cameras, it has inertial measurement units, and it navigates based using only those two sensors and a LiDAR to map the environment. As it turns the corner here, it finds out that the only way to get to the target is by entering this building. It adjusts to the change in contrast. It finds all these obstacles that are placed in the way by obliging DARPA program managers. And then as it turns the last corner, it detects the red object of interest right there. It happens to be a red barrel, and it goes back and reports to base. So I might be exaggerating just a little bit when I say, well, this is the kind of autonomy we're capable of doing. This happens to be in 3D, but you can also do it in 2D. I'll draw your attention to two things. The world is not changing. There are no human beings darting across here. The world is static, but it is very unstructured. Unlike a factory, I don't know where things are. I don't know where trees are growing. I don't know where buildings are. And it is possible to generate maps like this in real time. In fact, we do this under forests. And if you're interested on the right side, the three key pieces of technology are: how do you determine where you are, how fast you're moving, and how you're rotating, what angular velocity, et cetera. So there's a gigantic common filter-like algorithm that's running that estimates all of this. We build a local map, and then we have to plan a motion planning algorithm that runs for a dynamical system that lives in a 16-dimensional state space. We're navigating these forests, and at the end of the day, we want to be able to tell you how many trees are there and what's the volume of carbon in each tree. Let me go to the other end of the spectrum. These are large UAVs, which weigh in excess of about 3 kilos. On the other end of the spectrum, you have these honeybees that weigh just 3 grams. And we'd love to be able to create smaller vehicles. Why? Because when you create smaller vehicles, as you'll see on the bottom left, a planned mid-air collision at 1/20th the second speed, you'll find that these vehicles are capable of sustaining collisions. They're safer, inherently safer. And in some sense, that's how nature navigates at the smaller scale. So we'd love to be able to put the autonomy that you see in the larger vehicles on board these smaller vehicles. And I'll show you an example of how our approach to planning and navigation changes completely on the bottom center and bottom right, where you see these swarms of UAVs, I apologize for the sound, that are able to navigate without worrying too much about what obstacles are there in the way. They get to that destination. And again, as mechanical engineers, you can actually try to estimate the stability envelopes of the nonlinear controllers we design. And it turns out that it's everything that you see in terms of the basin of attraction and so on scales directly with the eigenvalues of the inertia ellipsoid. So the smaller the eigenvalues, the much larger your stability, and this kind of plays out there. So that's what my lab works on. And of course, as you scale things down, we can also think about collaborative systems. So we create, excuse me, I forgot to turn off the audio here. So we build swarms like this, again, operating without GPS, operating only with cameras. On the top right, you see environments that we've mocked up in our lab that are very close to the kinds of environments we expect in the nuclear reactors in Fukushima, 2 of which we still don't know what's inside. And so we had a preliminary collaboration with TEPCO to show feasibility of flying in extreme radiation and in foggy conditions with lots of with moisture and poor lighting conditions. And again, the idea that if you have lots and lots of swarms, you can do things much faster and accomplish tasks collaboratively, which you cannot do with individual vehicles. So this is the work we do. Now I want to go and talk a little bit about autonomy versus automation. And my apologies if I sound a bit pedantic here, but I thought it'd be useful to go through some of these attributes that we might use to distinguish between these two ends. So in my mind, when you have structured environments, as you see, for example, in the shop floor of a factory, you can think about automating things. You can think about mechanizing things. On the other hand, if you think about my living room, or if you think of an orchard or a forest, those are completely unstructured, very hard to tell upfront where things are. And that's where you really need autonomy. So automation, as engineers, we try to categorize the operating conditions. We build an envelope where we operate. An autonomy, in an ideal world, you want to be able to accommodate perturbations. In fact, large perturbations, and not necessarily require these operating conditions we all define. So this is where some of the challenges are. Ideally, in automation, you don't want human intervention. You want things to be automated. In autonomy, this is a little now mixed. And again, I'm going to speculate. What we really want is human-like decision-making. If you have human-like decision-making, as human beings, we can collaborate with autonomous systems. That's where we ideally want. And then finally, in automation, as engineers, I mean, the first thing we learn in engineering in a first math course is how to find the maximum of a function or minimum of a function. Optimization is built into our DNA, but as we've found out, particularly in the COVID times, along with that comes a loss of resilience. So if you have truly autonomous system, you can actually think about architecting and designing more resilient systems. And so that's the promise of autonomy on the right side. I want to go to autonomous vehicles, a very, very concrete example. And these are the definitions of autonomy. Actually, the SAE calls them automation. Levels of driving automation, level 0, the kinds of cars that perhaps you and I learned how to drive on with no automation. Levels 1 and 2 with partial automation, driver assistance, partial automation, to levels 3 and 4, which start getting a little fuzzy in their descriptions. And part of the reason is, as we get to more and more autonomous systems, we don't have a clear lexicon. We don't know how to articulate what an autonomous system means. Although as human beings, we internally have some notion of what that really means. But you see conditional automation, which is level 3, high automation, level 4, full automation, which means I get in, tell the car where I want to go, point A to point B, no matter where point B is, I'm able to go. That's full automation. And so one question is, can we do this? So I want to give you a little bit of history. This is the first autonomous car ever built. This was built in 1987 by Ernst Dickmanns. He tested this Mercedes on German autobahns, driving at some ridiculous speed, using cameras only, tracking lanes, compensating for the dynamics that come with high-speed maneuvering around curves. He did this in 1987. The reason we never hear about this, and instead we hear about all these predictions that are made, Tesla, Audi, and I just pulled ones from 2014 and after that, is because nobody wants to be told that this is a really, really hard problem. It is not magically throwing some AI at it. It is about designing, architecting robust systems. And the fact that there are smart people like Ernst Dickmanns who've been working on this for 35 years is not a story we're willing to tell if we want to raise money for our latest startup. So there's a little bit of intellectual dishonesty as we think about autonomy. And for some reason, if you look at the bottom, the latest thing that we're now hearing are robo-taxis, as though that somehow is a lot easier to do than fully autonomous cars. But the latest raises have been about robo-taxis with levels 3 to 5 autonomy. My apologies, I certainly didn't want to I just want to show you two examples of traffic. The left is from Napoli in Italy, level 5 automation. The right is from Mumbai in India. And this is what level 5 automation suggests, that I can drive in any condition. And by the way, if you think India is hopeless, which I happen to think from automated cars, it is hopeless. Italy maybe is worth doing, but I challenge you to look at any of the patterns you see on the left side, especially what this white car is doing, and try to formulate a set of rules that a self-driving car could execute autonomously and reliably. It is a very, very hard problem. On a more sobering note, this happened last week, the Tesla Model S crash. 2 people died on this. Ironically, a day after this tweet, where Elon Musk tweets that saying that the autopilot is now approaching 10 times lower chance of accident, presumably higher reliability than the average vehicle, in spite of the fact that there's no data on self-driving cars to proclaim this. Once again, I worry about statements like this as we are all exuberant about the future of engineering. And this one really hurts. This was Elaine Hertzberg. This is the last known picture taken of her. It was taken by the Uber car that ran her over. You can look at this picture. You can see that there's somebody trying to cross the road, and yet the systems in place did not recognize her. Of course, it was blamed on human error, which raises the question of how do we think about autonomy in these kinds of setting, and how do we think about safety, and how do we think about certifying them? If you talk to anybody in the Valley, they'll tell you, well, all that is changing. Why? Because each one of these self-driving cars is gathering data. So you look at Waymo, they've driven millions of miles. Same thing with Tesla. And of course, with this data, you can train high-end machine learning algorithms, which is now called AI. By the way, AI has been around for a long time, but I think the thing that has really changed now is our ability to assimilate these large data sets and really do statistical machine learning on large-scale data sets. And some fields have changed dramatically. So for example, if you think about computer vision, which is a prerequisite for self-driving cars, our ability to detect objects, our ability to recognize objects, to classify them, thanks to statistical machine learning is now, I would say, almost superhuman. So we're able to do that. Same thing if you have a personal assistant like Google Home or Siri, you know that speech recognition, not language recognition, but speech recognition has advanced quite a bit. And yet there's almost zero use of AI in physical systems, autonomy in driving, autonomy in drones, autonomy in industrial robots is virtually non-existent. This is a really, really hard problem. I want to show you this video of this 3-year-old child showing just amazing dexterity, hand-eye coordination, as he almost absent-mindedly assembles these Lego blocks. Today's robots are nowhere close to that. And so as I think about the future, and I really do want to wrap up and be on time, I see two challenges for the future. One is the general question of safety. And safety is a complicated issue. I wanted to unpack it a little bit and decompose it into 3 different issues. I think all 3 issues will resonate with an engineer. So one is verification. So how do I prove that a system satisfies certain properties? This is the basis of designing and architecting and testing systems. If I can't verify it, I don't have an answer to the simple question, did I build the system right? And the second question that follows is a question of trust. And this is about ensuring that a system meets its formal requirements. Does it have unwanted behaviors? Does it have consequences? And to me, that answers the fundamental question, did I build the system right? And the last one is security, which I think most of us have a good sense of, which is how do you prevent unintentional manipulation or intentional manipulation by adversarial parties, by unauthorized parties? This is one set of challenges. I think the second set of challenges have to do with jobs. We know that AI and robotics will enable some kind of automation. Whether it's good automation or not, we don't know. To what extent we can push it, we don't know. And that's what is exciting about this century. But the other way I think as engineers we should think about is how do we design these technologies? Sorry, Dan. How do we design these engineered systems to help humans? And so there's this fundamental concept of trying to augment what humans can do, what humans are able to do with their intelligence, which we can call intelligence augmentation. So at the end of the day, really what we should be thinking about is IA, intelligence augmentation, and not AI, which is artificial intelligence. The only thing true about AI is the A piece, it's artificial. I don't believe that it's about intelligence at all. So as we think about systems that we might architect that truly benefit mankind, I think the question we should ask is what kind of intelligent systems that can we build that can benefit humans, lead better lives. I want to thank you. And again, what an honor it's been to be at the same podium, the same Zoom screen with Dan Mote. Dan, congratulations once more. Thank you for inspiring a whole new generation of engineers.
Hey, thanks a lot, Vijay. This was awesome. It was a great exposition on the very broad field of autonomy and robotics. I have my head is bursting with questions, but I'm going to have to wait in line with the Q&A for the Q&A session. I was just going to say I was just reminded of an article I read recently by one of those die-hard naval engineers. The title was "Artificial Stupidity," because he's very skeptical of what so-called AI can do to the system, and I think I could hear echoes of that in your talk. So I'd love to get more from you during the Q&A. Next, I would like to present Dr. Rashid Bashir. Again, this is a very brief bio. Professor Bashir is Dean of Engineering, the Grainger Distinguished Chair in Engineering, and Professor of Bioengineering at the University of Illinois at Urbana-Champaign. Prior to joining UIUC, he was at Purdue University. Earlier to that, he worked at National Semiconductor Corporation in Santa Clara as a senior engineering manager. He was a member of the core founding team for Illinois College of Medicine at the University of Illinois at Urbana-Champaign. So he comes to this panel with a diverse experience. He graduated with a PhD in electrical engineering from Purdue. He's a fellow of IEEE, AIMBE, AAAS, BMES, IAMBE, RSCAPS, and NAI. My God, Rashid. Using bio-nanotechnology, biomems, and lab on a chip, he's working at the interface of biology and engineering from the molecular to the tissue scale, and aims to make makes a big impact on grand challenges in health and medicine.
Thank you.
It's all yours, Rashid.
All right, thank you very much. Can you hear me and see the slides okay?
Yep.
Great. Well, thank you so much. This is a great honor to be able to present at the symposium. My title of my talk is very broad: bioengineering. I would say bioengineering and medicine, or bioengineering of medicine, and really engineering at the service of humanity. And first and foremost, of course, I want to congratulate Professor Dan Mote. I've met him before a couple times. I don't know if he remembers or not, but it's just a tremendous honor to be able to speak at the symposium honoring his contributions and the award of the 2021 Franklin Medal in Mechanical Engineering. So congratulations, Dan. I'm going to give you a couple of broad thoughts and also throw in our own work in between. So I do believe that this century is a century of engineering, and also as engineering interfaces to biology and medicine. We know global population is expected to rise, reach about 9 billion by about 2050. And people are living longer and want to live healthier, which is great. By 2050, the number of the percent of people over 85 will double, the percent of people over 65 will quadruple. And I think in 2047, we'll have more people over 65 than we'll have under 25. So, aging, and I won't get to talk a lot about it, but as you can imagine, that's a tremendous grand challenge in terms of especially the conditions and diseases that are going to be connected to aging. So I think this convergence of medicine, biology, and engineering is one of the next major frontiers. And a simple question is, can we do for medicine what engineering did for many other industries? And that is still a dream to be fulfilled that has not been accomplished, of course. So what I'll just show is this one article that I had a pleasure of writing a perspective with Xu Chen, Bob Nerum, and Roderick Pettigrew, which I'll just quote this one line from it, which is, we posit that the integration of engineering into medicine and medicine into engineering until the boundaries vanish will play a critical role in achieving these broad and specific goals. And the broad and specific goals include higher quality healthcare, reducing cost, and increasing quality. It's called the triple aim in medicine. I also refer you to this wonderful report on convergence on the future of health from MIT that was published some years ago. So, let me talk about a couple of the challenges. You've probably seen some of this, but it's really still staggering. Of course, the cost of healthcare in the US are unsustainable. Our expenditures on healthcare as percent of GDPs are shown here. We're about 18% as of even just a year or two ago, and we are about 2x that of other developed countries. So, again, this triple aim that I mentioned earlier, and figuring out how we really use broadly engineering and design, and yes, some aspects of technology to really advance the practice of healthcare. Let me also mention a couple of other facts that might be of interest. So first of all, in the US still, the leading cause of death is heart disease and cancer next. But of course, this year, we won't be giving a talk without mentioning COVID, of course, and my heart goes to everybody that's been impacted by this terrible disease and continues to be, especially in countries, as you know, in India. This is just a tremendous problem as we speak, and many countries around the world. So, COVID-19 this past year was the third leading cause of death. And then another stat that I want to show, which again highlights for the need of engineering, is that actually the medical errors actually is the third leading cause outside of COVID for lives, for causing death. So the need for this, I think, to me, really highlights the need for healthcare systems engineering, process optimization, and modernization of this industry. I say, as an engineering dean also, the only domain we don't have free access to is healthcare. Any other domain, electrical, mechanical, civil, chemical, we have access to that industry, to that domain. But healthcare, we don't have, and for good reason, because lives are at stake. But however, how do we break that barrier to penetrate and work together to really advance healthcare? One other a passion of mine, this is also a work in this area, is sepsis. And I wanted to highlight this also, some stats here. Sepsis is something that doesn't have the visibility that it should. And again, all these other conditions are really important, but sepsis, believe it or not, 1 in 3 people that die in hospitals actually have sepsis. They usually have confounding, multiple conditions. But sepsis, go look at the CDC website and just do some searches. It is just amazing. It's the leading cause of death in critical care in the US and the world, estimated over 26 billion annual cost, the most expensive condition and the leading cause of readmissions into hospitals. So I want to highlight these things just kind of at a glance to really to the next generation, that these are the challenges that exist today that we need engineers to work on. And this view of sort of personalized medicine, what's called personalized medicine over the last 10 years or so, but this idea of, let's say, taking samples from patients, being able to rapidly detect the source of pathogen, whether it's a bacteria, virus, or fungi, at the same time, being able to take that body fluid and profile the immune system, the status of the immune system. Everybody's immune system is different, and the immune system responds differently to the insult from the infection. And we're seeing that with COVID-19, of course. Something that is not well understood is that why certain people can get through it and why certain people can't. If you can isolate that pathogen, then you like to be able to do drug susceptibility testing, and then based on all of that, do a therapeutic management back to the patient. So this is kind of a holistic view of personalized medicine, and the same general idea I'll show you applies to cancer also. But one very important thing that I know Vijay just mentioned also is this, of course, data analytics, machine learning, and AI, or IA, where how do you learn from these experiences? How do we collect the data to be able to learn from all of that, synthesize that information, and provide that information to the physicians to make a more informed decision, right? Physicians shouldn't make a decision based on their own experience. They should make the decision based on thousands of physicians' experience, right? And how do we get there? And as I always say, I mean, AI will not replace physicians, but physicians who don't know AI will be replaced. Let me also just mention what happens in this particular case of infection care and management today in the hospital, and some major challenges in that space is that this identification of the pathogen as early as possible. This is still a grand challenge, especially if you're talking about bacterial pathogens. The culture method, which is still the gold standard, takes up to 5 days for a confirmed negative. So you start a bacterial culture, a blood culture, or urine culture, looking for bacteria to grow, and that you continue that, and of course physicians can't wait for that, so they go ahead and make decisions. But if there is a way to reduce those 5 days down to a few hours or less, this would be a huge impact to the field of infectious diseases diagnosis. Bacterial culture takes too long, and it's a sampling problem. You are taking a small volume of blood, and so you're not able to at times sample the bacteria that might be in the body. How do you quantitatively profile the patient immune system over time? This is just very important because everybody's immune system responds differently. And then how do you prioritize and stratify antibiotic treatment? Today we are, overly medicating patients. We know that. And as a result, there is also a risk of developing, of course, antibiotic resistance. Just very quickly, I think this is a busy slide, but to show that point of care sensors are gonna, I think, continue to advance. This past year actually has given us all and FDA a major push to move various types of point of care sensors out in the market. As of right now, there are 4 point-of-care sensors that got the EUA approval. And it was interesting, those companies were working to push those through for the last 7 or 8 years. And within a year, because of the crisis, their technologies got moved through and got EUA approval. And we hope that they will be available. Similarly, three antigen tests also got approved this past year by companies that were working on those for many, many, many years. Our work here, we're trying to measure cells and molecules at the same time from a drop of blood using microfluidic devices in these cartridges. And we have demonstrated a range of sort of applications here for CD4, CD8, and CD64. These are white blood cells that are indicative of the immune response and various conditions. And what's exciting about this technology is that we can also measure protein biomarkers from the same sample. I just very briefly mentioned this past year, of course, since my own work is in this space, we obviously couldn't sit back, and we also developed a rapid diagnostics for SARS-CoV-2 that we're in the process of trying to commercialize. But we took samples, of course, from the viral transport media with the swab-based method and compared this also to saliva, which we believe is perhaps even a more improved sample source for looking for respiratory viruses like SARS-CoV-2. We were able to work with Bill King and others to develop these additively manufactured cartridges, and then develop these devices, which we use cell phone camera to look for fluorescence increase and compare this data from viral transport media and saliva, and they look very similar. And again, a big clinical team, thanks to our clinical partners from Carl and OSF Healthcare. This idea of personalized medicine, I want to show a very similar sort of an approach, but that has actually been more applied towards cancer. How do can you take a solid or liquid biopsy from the patient, perform a molecular analysis of that tumor? And this, by the way, the cost of doing a full sequencing for genome now is about $1,500. So that's another dramatically impactful technology that I didn't get to mention a whole lot here, but that's used now routinely. And then the idea of taking a sample from the patient and expanding that to create clones of what we call maybe microorganoids or microcancers, and then do drug screening on those. And then also, of course, imaging and other measurements, and put it all together to then stratify and provide the therapy to the patient. This is a collaboration we have with Mayo Clinic, but folks at Mayo are really leading the charge on this, my colleague George Westmatzis, and the goal is, can you do this entire process in a week? So currently it takes many months to do this, maybe even a month and a half. Can you do this in a whole week? Just, within a week. So this is really a systems engineering problem where you got to put all these things together and optimize and speed up the processes. Towards this end, we had a paper that just actually came out this past week on creating these micro-cancer organoids on an array. You can see these little spheres. These are about 500 cells per well, and then we can image them and do drug studies, and within a few days be able to determine whether the cells are live or not. So I think there is a lot of advances in this area. I want to also mention another new direction, which is this idea of biological machines on robotics. And of course, Vijay just mentioned some of sort of the inspiration from nature, but can you, we have already demonstrated this, but we can 3D print, let's say, scaffolds with hydrogels and polymers, grow muscle cells on these, and these muscle cells, these particular ones have channel rhodopsin transfected in them, so they're light sensitive. So now I can forward design this centimeter scale biological robot that crawls on a petri dish in fluid when you shine light on it. So it's light controlled actuation that's biologically driven essentially. And you can make all sorts of structures now. We're teaching this in our undergraduate labs here in bioengineering, where we give students some design rules, and then they can go ahead and fabricate different kind of actuators that are all cell powered and cell driven. Similarly, the field of tissue engineering is advanced to a point where you can start to forward design structures. So here, just very quickly on the top right, these are human-induced stem cell differentiated motor neurons that then can be shaped into different topologies, different geometries. This is a rod, is a ring, and you can put these rings, of course, on a MEA, microelectrode array, measure activity, but also these are optogenetically transfected, so you can shine light on one part of this ring and measure the electrical activity on the other part of the ring, indicating that there is connectivity through the neuronal cells that are within that structure. So, if we can fabricate things like that, and actually it's really interesting, Vijay showed a video of honeybees, we have one of the leaders of, honeybee sort of biology on our campus here, Gene Robinson, was talking to him just the other day about, it's pretty amazing what a honeybee can do with a millimeter cube size brain. So couldn't we start thinking about forward designing biological processor based on living tissue, based on living cells? Can we put neurons in the right configuration now in a three-dimensional topology with inputs and outputs to be able to let's say, create a brain in vitro or a mind in vitro? So I think these are the directions that I believe are really exciting, where the engineering mindset is applied to building systems and devices that are composed of biological components. Hyper organs. So we want to definitely replicate organs, but why stop there? Why not think about adding functionalities that don't naturally exist? Can I design blood vessels that not only just provide fluid transport, but rather can sense the buildup of pressure and hence start pumping, for example? So there is, I think, this idea of forward design, which is, I believe, is really engineering. That's, applying that to biological systems is clearly a major frontier. And this is maybe a very simplistic way to kind of, my view of, and I hope this aligns with what Professor Mote said earlier too very much, but I mean, engineering is really, the translation of the laws of physics and chemistry into forward design. That there are laws, I can use those laws to design forward. That's really the difference. It's just a title. It's just a name. I think over time, the knowledge will advance to a point where we'll be able to forward design more and more in biology. And it's already happening, right? That's what synthetic biology is. Synthetic biology is the forward design of biological systems, right? And I think the question is also, how do we advance that to health and medicine? And one thing let me mention here is that certainly any systems you want to design that relate to medicine and health, you have to absolutely bring in the social sciences and look at the social and behavioral disparities and the social and behavioral determinants of health also. It's really critical to collaborate across that realm. And finally, let me just I think mention this. As we were talking about all of this, we had this opportunity to think about medical education here on our campus, and the hypothesis was quite simple. That just like you can't be a physicist or an engineer without knowing math, we believe that you can't be a physician of the future or physician leader of the future if you don't know engineering. And if that's a hypothesis, then why don't we include the engineering and engineering mindset in the medical curriculum? So current medical curriculum is based on biological sciences and clinical sciences, of course, grounded and sort of, homed into patient care and compassion. Which is really critical. But then why wouldn't we think about adding this component as a third pillar of innovation, design, entrepreneurship, and engineering sciences and technology? And we believe this is the future of medical curriculum. So we started a new med school, as I'm sure all of you know, on this idea, which is now actually in its third year. And it really brings together every course in this med school has been developed by three individuals: a basic scientist, a clinician, and an engineer / computer scientist. So we have engineering faculty are teaching a third of this curriculum in this med school. It's called the Carl Illinois College of Medicine. We believe it's the world's first medical school where engineering is really fused in from the bottom up all the way across the 4 years. We have achieved provisional accreditation and admitted 3 classes. And there's some really exciting sort of design projects and idea projects out of every clerkship that engineering faculty do rounds with the clinical clerkship director. And then every medical student has to do a capstone project and a data science project. So with that, I will stop and really talk about the fact that I know I speak this for all of our certainly leadership in academia, but leadership through service. I think collaboration is really so important to address these major challenges that really need to bring teams of people. and love, of course, we all want to engineer the world to be a better place for the service of humanity and for the next generation. Thank you very much. I'll stop there.
Thank you so much, Rashid. This was awesome. I work myself at the intersection of engineering and medicine, especially in analytics, and I'm just trying to understand integrate physiology. And to me, your work is very inspiring and amazing, and almost feels like science fiction. And also want to really congratulate you on the education initiative. I'm also kind of working with a couple of MD, PhD students, and both came from strong physics backgrounds, and they're both expressed fear that they're losing that analytical thinking when they're going through med school, and that's ridiculous, right? So and whatever they had, they're losing. It's not a question of even getting better at it. So appreciate your talk. It's awesome. So if it's okay with you, we'll go ahead with Dr. Majumdar next, and we'll take a break after that. Dr. Majumdar is the J. Precourt Provostial Chair Professor at Stanford and is a faculty member of the Department of Mechanical Engineering. From 2009 to 2012, Dr. Majumdar served as the founding director of ARPA-E, and over the next year as the acting Undersecretary of Energy. After leaving Washington, D.C., Dr. Majumdar was the VP for Energy at Google, and he's a member of the National Academy of Sciences, National Academy of Engineering, and the American Academy of Arts and Sciences. He served as Vice Chairman of the Advisory Board to the U.S. Secretary of Energy and a Science Envoy from the U.S. Department of State for the U.S. Department of State, and serves on the Advisory Board of numerous nonprofits. He received his BS in Mechanical Engineering from IIT Bombay and his PhD from University of California, Berkeley. Arun, want to go ahead?
Well, thank you. First of all, thank you for inviting me to this very distinguished group of people. And I want to take this opportunity to congratulate Dan for, just the leadership that he has provided to the whole field of engineering and his friendship over the years. Some of you may not know, he was the vice chair for graduate studies who signed the letter and gave me admission to UC Berkeley as a graduate student. So if anyone has any problems with me, you can blame Dan for letting me in out here. But it's been just a wonderful friendship in working with Dan over many years, and I appreciate the opportunity to talk about energy and environment. Let me share my slides. Let me see if, okay, does it show up now?
It's showing up, but not in full screen mode. Yeah, there you go.
Okay.
It was there for a second.
Let me see if I can. It's not in full screen mode now?
No, it's not.
Okay. Somehow.
Oh, it's for a flash, it came on and then went back to.
Ouch.
Just maybe there's a lag. Don't click it again. Let's see.
How about now?
Nah. Dan Ehert, do you have a solution from our IT? Or Jeff? Oh, it was there for a second.
How about if would this be okay?
Yeah, I think it's fine. Let's just go ahead. Yeah.
Okay.
Oh, this is good. That's good. Let's go for this.
So energy and climate, I'd like to just sort of note that this, I believe, is the defining issue of the 21st century. And the reason being is that it affects everything. Just to give you a historical perspective on this, sorry, my slide deck is not quite working. I'm not sure exactly why. Let me try again. Is it showing now?
Yes, we are seeing your slide.
Full slide deck? The whole screen?
It looks like it.
Okay.
I think
Actually,
it's
more
cut
like
off on the side.
90% of it.
Okay, let me. Give me 1 second. Sorry about this.
Hey, Dan, do you have a solution to this? Do you know what's going on?
Not, no, I'm looking right now. I'm not sure.
Okay. Let me try again.
Well, Arun, we could do one thing.
Yeah.
We could take the break now.
Yeah. Why don't we do that?
And then we resolve this issue so that, and then we can come back. So
thank you. Appreciate it.
So worst case, you email it to me and I'll share it, or Dan or somebody. So okay, folks. So let's take a 10-minute break. Remember to populate the questions, and we will get to them in order. And so it's right now for our time here in the East Coast is 10:35. So we'll reconvene at around 10:45. Thank you. So, Arun, I already gave you an introduction. I'm sorry. Yeah. Okay. So go ahead.
Thank you, Lord. Energy and climate, I feel that it is the defining issue of the 21st century, and let me explain why. First, let me show you the population curve. Whoops, something, it's not advancing now. Oh, no. Okay. This is the population growth in the world. And as we know, engineering is about people. And so it's important to note how many are there. And over the years, you can think of this, as far as the Earth is concerned, this is the population, the human tsunami that has happened on the world. And this population is leveling out. By the end of the century, it'll be about 10 billion people, 10 to 11 billion people. Right now, we have about close to 8 billion people. So add another, China plus India together, and that's the population by the end of the century. But in addition to the exponential population growth, there has been another exponential, that is the per capita GDP of the world has gone up exponentially. And GDP sometimes is used as a prosperity of people or quality of life, but frankly, when the gentleman who actually invented GDP in 1933 warned people about whether GDP should be used about the welfare of people. Human Development Index now is a better measure. Nevertheless, what has happened over the last 150 years is an amazing, in the short history, but in the history of humankind, it has been an amazing period, because there's been no such period in the past like this. And so if you look at where we are and where we have come from over the last 150 years, we used to live mostly in this kind of a society, agrarian society, in villages and growing food and livestock. And from here, and we used to travel using animal power. From here, this is where we are today in 150 years. Electric lit and air-conditioned homes. We can watch television. We have healthcare, as was just discussed. Our life expectancy has gone up by a factor of 2. We have the information of the world on our fingertips, and we can travel to a grocery store with 100 horses in our engine, or travel across the world in 100,000 horses. This amazing feat, in most of it in the last 100 years, is what we call the Industrial Revolution, and it is still ongoing, and what I call horsepower to horsepower. That is what has happened, and it is all powered by energy. If you take energy away, it goes away. And in fact, if you look at our lives today, in everything, pretty much everything we do, whether it's communication, as we are now doing, or whether the food that we eat, or the clothes that we wear, or the steel and cement that goes into our buildings, if you take energy away, none of that actually happens. So it is the foundation of any modern economy. And if you look at the history, this revolution also coincides with the energy revolution, which is we used to use all biomass, and today we use 80% of our energy comes from fossil energy. Very little from hydro, and renewables are growing very fast, but it is still a very small percentage. And of course, this has consequences. And the consequences, I think, are well known now. The global average temperature rise has gone up by a degree because of the CO2, anthropogenic CO2 in the atmosphere. And because of this, we are getting extremes in our weather patterns. It's climate-induced weather extremes. And so this global average temperature rise is misleading because it is not uniform across the whole world. If you look at what's going on in the poles, the poles are warming even faster. The sea ice extent has gone down in the Arctic very sharply, and it is accelerating. And it's not just the sea ice, the land ice is going down. And one may think that, oh, this is of the poles, it doesn't affect us. It actually does, because these are the global average temperatures of summers around the Earth. And you can see it looks like a nice Gaussian. Some summers are hot, some summers are cool. But over the years, this distribution is moving to the right. And you'll find that the probability of getting a 4 sigma or a 5 sigma event is not once in 100 years, once in 10 years now. And that is what has happened. And it is not a Gaussian tail, it is a long tail. And when you get the tail, it affects disproportionately compared to the average. And so it is the tails that we're really worried about, the tails of the distribution affecting us, because once that happens, whether you have a heat wave or a cold wave, it really adversely affects humanity. And it is not a surprise that the all-time high temperatures around the world has happened only in the last few years. And so this is not going away. And the question is, what do we do about it? So let me give you the sense of sort of timing through a pop quiz. So I'm going to throw you some numbers. I want you to guess what the units are and what it means. But there's no grading. I mean, there's no pressure on this one. So the first number is 1. And this is 1 degree Celsius. It's actually 1.1 or 1.2. This is the global average temperature rise since the pre-industrial levels. And we are seeing the extremes based on that right now. The second number is 2. This is 2 degrees Celsius. This is the Paris Agreement that we have now rejoined, because we felt, the world felt, that if 1 degree can give you these kinds of extremes, 2 degrees will be even worse. And I don't think we should let the world go beyond 2 degrees, the global average temperature rise. The third number is 800. It's not 800 degrees Celsius, don't worry. It's not Venus. But if you are to keep the global average temperature rise below 2 degrees Celsius, we have a carbon budget of 800 billion tons of CO2 left for the world to emit. Because if you cross that, you're going to likely to cross 2 degrees Celsius. The fourth number is 40. This is 40 gigatons of CO2 per year. This is the global emissions per year, 40 gigatons. Just to give you an idea of how much is a gigaton, if you add up the weight of all human beings on this earth, the 8 billion human beings on this earth, if you add up the weight, it's less than a gigaton. It's about 0.6 gigatons. And we are emitting 40 gigatons of CO2 per year. And of course, the last number is 20. We've got 20 years left. And after that, and this is assuming that you keep it at 40 gigatons, although the emissions are now going up, except for the COVID last year. So this is where we are. There's a sense of urgency, a fierce urgency that we have to address this. And where do the emissions come from? Clearly, electricity and heat production is a big deal, 25%. And transportation, we believe, is a big one, 14%. Industry, which is mostly steel, cement, and petrochemicals, is 21%. But what is often forgotten is agriculture and forestry. Agriculture, what we eat, really makes a difference. Whether we eat meat or whether we eat vegetables has a huge, huge difference. And so that is 24%, 10% more than transportation. So I wanted to give you, this is, if you are to address this, it is addressing almost the whole economy. And so this is a major shift in the 21st century. And the next decade, I feel, ought to be the roaring 20s of the 21st century for a clean and sustainable energy. So that's all, it's scary. But what's the good news? there are some three good news I think it's worth noting. One is the unconventional gas. Now, one may think, oh, this is fossil fuel. It is true. It is not a permanent solution, but it's displacing coal. And frankly, it's allowing a lot of things to go away from coal, not just in the United States, but in other parts of the world. But it is a temporary solution. The biggest solution, and this is one of the grand challenges that Dan talked about, is the cost of solar electricity generation is now the cheapest way to produce electricity, solar and wind. And that is the yellow are the solar, the blue is the wind, and the dashed black line is electricity from natural gas, from combined cycle turbines, which operate at 60% efficiency. And solar and wind is already in many parts of the world and will become all over the world the cheapest way to produce electricity in the next few years. And it has already happened within the last decade. So this is an amazing feat. Now, the challenge is the grid. The electricity grid was never designed. The Tesla Edison grid architecture was never designed for fluctuating wind and solar. And that's a major issue. We can talk about that, and I'll talk about that in a minute. The third one is the cost reduction in lithium-ion batteries. And this has come down by a factor of almost 10 in a decade. It is at about $125 per kilowatt hour. If it reaches $100 a kilowatt hour, the range of electric vehicle and the cost of electric vehicle becomes competitive with gasoline cars and with much less maintenance and much bigger power, torque. And so we feel that this, in the next few years, it'll be difficult for people. One has to think whether you want to buy a gasoline car for the next decade or you want to buy an electric car. This is a tectonic shift in the automotive industry, and people poo-pooed Tesla for a long time because that's, it's never going to fly. It is the largest car company today in the world. And now GM has announced, it took them a while, GM has announced that they're going to go all electric. Volkswagen, Toyota, and all are announcing that. This, after 100 years of internal combustion engine, this is a tectonic shift in the automotive industry. Of course, the electricity has to be carbon-free, otherwise you'll be polluting more. But nevertheless, these breakthroughs are really changing the landscape. But the problem is that given the scale of the issue of energy and climate, this is necessary but not sufficient. The question is, what else is needed? There's a lot more. We don't have storage solutions, long duration storage for the grid, and that has to be at 1/10 the cost of lithium-ion batteries. Lithium-ion cannot do this. Our nuclear, which is very important it's the largest source of carbon-free power in the United States and many parts of the world, and that cost is going up as we scale more, and that's in the wrong direction, and we need to bring down that cost. Refrigerants for air conditioning, they have a global warming potential 2,000 to 3,000 times that of CO2. And according to the Kigali Agreement, which is 1 year after the Paris Agreement, these refrigerants will be phased out. And we don't really have the drop-in technology yet. And zero net energy buildings, which is fantastic, but trying to do this at zero net cost is where it's become scalable. I talked about industry, whether it's steel, cement, petrochemicals, and the use of hydrogen, carbon-free hydrogen to do this. It's going to be very important. And of course, decarbonizing food and agriculture, including food waste. And in addition to that, the carbon management of sucking out CO2 from the atmosphere and putting it underground, all scenarios have said that if you want to keep ourselves below 2 degrees, you need some kind of either natural solution like photosynthetic, harnessing the biological cycle, or direct air capture, because if you don't have negative emissions, we're unlikely to keep 2 degrees Celsius. That's the magnitude of the problem. So let me just say this, that whatever 10 billion people consume will produce a gigaton scale effect. And that is electricity, heating and cooling, transportation, food, textile, water, steel, cement, and information. And so if you step back for a moment in this, you look at the world, where it's going, and we are in the hinge of history right now. And the best way to describe it is, according to an engineer who described it in his own ways, in his own world, but I like to use this in this moment in time. And that is, the words of Andy Grove, who, as you know, was a fantastic engineer and the former CEO of Intel. He wrote a book called Only the Paranoid Survive. And in that book, he described something called a strategic inflection point. And he was describing for Intel, but in his book, he generalized it for a business, for an industry, for the world, for all of us. And the inflection point is the following. The point in the life of a business or an industry, in this case, the world, when its fundamentals are about to change. The change can mean an opportunity to rise to new heights, but it may just as likely signal the beginning of the end. Now, the question is, can we pivot? Can we switch around? And so this is the strategic inflection point, where it has been induced by the breakthroughs that are happening in the energy industry, as well as the climate-induced 2 degrees Celsius. Because if GM decided not to change, they may end up down there, as opposed to they may actually go up right now if they are deciding to change. So this is the inflection point that we're talking about. And so how do we address a strategic inflection point like this? Because there's no going backwards in time to use data to figure out what we're going to do in the future, because going back to the 20th century solution, that's what got us here. So we have to figure out how to navigate this landscape and how to address the strategic inflection point. And the only way I can think of is to look at, you have to experiment. You got to try out new ideas, new solutions, leverage other technologies into these areas. Look for first adopters, look for new markets. This is the time to experiment, and there'll be some failures. But we have to take some calculated risks. We have to fail quickly, learn from those failures, and be connected to each other so that we know other people's mistakes and we don't repeat them. We need to, there will be competition. The previous competitors could become partners and new competitors may arise. We need to be flexible and agile to be able to move around because things are shifting. And clearly there's need for startups, but the most difficult part is scale up. And the execution and the vision of people involved in this, critically important. And of course, we need talent and capital needed. What I'm describing to you is the innovation ecosystem. And that is what we need. We need to innovate ourselves out of this. And that needs fundamentals in science and engineering to create new breakthroughs that I just talked about. Let me end here by saying this has been a great opportunity to speak, and thank you for inviting me. But this is what we are talking about. This is our future generations, and what we leave behind is going to be critically important for them to take the baton and create a world, as Dan described, that is sustainable. And it's not just the human beings, but the whole earth. Thank you very much.
Well, thank you, Arun, for a very lucid and a little scary presentation on energy in the environment. So I guess we're going to see a lot of upheavals in the coming years. So it gives us a lot of things to talk about. So I want to thank all the speakers for their inspiring talks. I think this is the time that we could perhaps have for have some discussion. So let me see what we have here. So the first question, I guess, is for everybody, but Dan kind of posed this in the beginning. Is it possible for engineering education to change radically? Could basic subjects such as calculus be given less emphasis in favor of more practical solutions for our planet? So I guess the question is, maybe if I could take the liberty of rephrasing it, is how does engineering education need to change in the light of what we are talking about? And I think some of that was addressed by, I think, all of you. But perhaps, Dan, you want to take a shot at that?
Well, the answer is yes, of course. I mean, look how much engineering education has changed in the last 100 years. I mean, it's like nothing before. In fact, even in the last 20 years, engineering has changed like nothing before, actually. And but I think the leadership of education has to do it. It's going to happen at the dean's level and the president's level at universities. If they don't get it, we have a problem. And I think most of them, as far as I can tell, don't get it currently. But I'll give you a good example. But the current president of Maryland, Daryl Pines, also a Berkeley graduate, by the way. In fact, I was his undergraduate advisor, as a matter of fact. This is a funny story by itself. Anyway, so I'm now working for him. And he got a $22 million gift from Jim Clark's family when Jim Clark died, a very eminent guy and a Maryland graduate and so on, wonderful person. But the Clark Foundation, when they provided the money, they didn't know about engineering and they didn't know about universities at all. So they were just business people. So they asked Daryl Pines, they asked him to come and advise them on how they should give this money away that would be most useful. And so he went there. And one of the things he told them, he says, okay, you're going to give us $20 million or something like that. But you've got to give $2 or $3 million at least has to go to the rest of the campus, not just to engineering. Cannot go just to engineering. It has to go to humanities, social sciences, and so forth. And he actually worked it out for them, and they agreed. Whatever he wanted to do, they agreed to. So that's what happened. Well, those departments were thrilled because they don't get money to start with very often, and then they don't get it from engineering, especially because engineering is always, on the edge of the campus. It's always a sideline operation, sort of like business schools or law schools and things like that, medical schools even. So they're on the edges of the campus, not really the campus. So what I'm trying to say is you have to change the culture of the campuses in order to bring in a broader perspective. Now you have engineering students who really like supporting people in society. In fact, it's one of their first questions. How do I do that? How can I engage in that? God, when I was a student, that's the last thing you ever thought of. In fact, as I said, a lot of people went into engineering, so they didn't have to deal with people in society. It was a kind of a benefit when I was a student not to do that. So I think the change has to happen, and I think it has to be led by engineering schools, because that's where the base is. That's where the education is. That the whole culture is established by engineering schools, and but I think first of all the schools have to realize it's necessary. I mean, they have to see that needs to be done. Once they decide to do it, they can do it. But until they decide to do it, they won't do it. So I think that's why we need to think of it. So I think organizations like the Franklin Foundation, Ben Franklin Institute, organizations like this can help lead that idea of transformation. I think it's highly possible, and I think it could happen rather fast if people decide to do it.
Please.
Yeah, so I can jump in here. So I think, this is a really important question. I mean, if you look at engineering disciplines or the various sort of undergraduate programs that we talk about, or the departments that how we are organized, right? I would say the three newest disciplines that, in the field of engineering and the leadership of engineering decided to have undergraduate departments in the last 30 years are, right, material science, right? Material science and engineering came out of, metallurgy, physics, mechanics, so to speak, bioengineering, and environmental engineering. I would say those maybe are the three newest engineering undergraduate degrees that might be given at various institutions across the country, right? So I do think we need to be thinking about kind of what's next that can be taught with the firm foundations of math and physics and chemistry, perhaps increasingly biology, and now data science, by the way. That discussion is happening, as you all know, at all places. How do we integrate data science as another pillar, foundational pillar? But then I think the question here is how do you balance that, right, versus a mission-driven, a degree on on energy, a degree on cancer, a degree on undergraduate degree. So I think that's a debate that'll continue on. But I do believe that we have to still make sure that the foundations are somehow there in its strongest form. And add new foundations that then become the base or the multiple pillars on which to stand up and go after the mission-driven challenges, perhaps in the third and fourth year, if they are to be brought into undergraduate education. I mean, we've been thinking about that. Actually, our bioengineering department here is starting a new degree in neural engineering, undergraduate degree in neural engineering, because we felt like the brain as a whole is a frontier, is a major frontier for decades and decades to come. So perhaps it warrants an undergraduate degree that's still based on sort of bioengineering type principles, but then is more domain specific, right? So I think that's really the question, and I certainly would love to hear from others, but I think one has to make sure that the fundamentals are there on which to build upon the application and mission-driven areas, right? And one example, I'll tell you one other thing around computing and data. We have this idea of computing integrated into all majors. We have actually a program here called CS plus X, where X could be any majors. And this past year, we had more applicants in CS plus X's than in CS, because there was sort of space and availability in those units. And now there's 16 CS plus X's. So new undergraduate majors in CS plus music, CS plus history, CS plus advertising, CS plus linguistics. So I think it's a really good question, and like Professor Mote said, we got to keep thinking about how to integrate these new foundational elements, and then how do you balance it with the mission-driven, which is really the core of the question. How do you balance it with the mission-driven practical solutions for our planet? And whether it's undergraduate education or whether you have to start doing that, I do believe also is lifelong learning and being able to provide and develop modules and certificates or other things that we continue on learning over time, right? That is actually part of the discussion has to be around that too, is that how do you provide that new knowledge to all the others who are still, who got their undergraduate years ago, right? So I'll stop there.
So I would just go ahead, Michelle.
Yeah, Rashid, I appreciate all of these points. And I think where we are now in engineering education is that we do have a lot more disciplines that may warrant their own majors, as you're talking about, or interdisciplinary associations of majors like CS plus X, which is brilliant. But for things like sustainability, which we were talking about with Arun, what we've been doing at Villanova is to weave sustainable practices and sustainable concepts throughout our entire engineering curriculum, so that when you're taught engineering, you're taught engineering as a sustainable engineer. It's not an afterthought, oh yeah, and let's make it sustainable. It is the way you engineer. And we're trying to instill that through our entire curriculum. We spent about the last decade here at Villanova instilling the principles of an entrepreneurial mindset to look at and weaving some of those throughout the curriculum. So in some ways for our undergrads, I think you can integrate some of these philosophies and principles into what an engineer is defined as. And of course, in others, you need to create whole new fields and disciplines. It's a very interesting time to prepare for the next century.
I was just going to say, so the kind of jumping on Michelle's point, the integration is important. And our former dean, Dr. Barry Johnson, I'll borrow a line he used to say the engineering is the liberal arts of the 21st century. So his point was exactly what I think one of the speakers made, which is that engineering needs to be integrated in the curriculum of other disciplines. So it's a two-way thing. Engineers need to understand the liberal arts, concepts of societal aspects, the ethics. Ethics cannot be taught as a course. Here you take an ethics class and now we go practice engineering. That's kind of silly. It has to be integrated into the curriculum in terms of, and all this environmental ethics is taught as a course. What does it even mean? And then you do that and you do whatever you want, right? So I just going to make that point, that there needs to be the point that Professor Mote was making, both physically and metaphysically, engineering needs to be integrated on campus. It needs to be sort of part of this whole picture. So there's maybe we can move on to something else if anybody else has any comments on this. Or so this is a very interesting question. I think it might be Professor Alsoy who posed this. Science is a well-known scientific method. Dan, I think this is especially for you because you pointed out science is different from engineering. So science is a well-known scientific method. Is there an equivalent engineering method? And what are the implications for engineering education again?
Are you talking to me now, by the way?
I think yeah, it's not the other Dan, it's you.
Well, no, I don't think there's a look at the science it's actually, if you look at the essence of science, it's actually very narrow, right? It's talking about fundamental phenomenon, first of all. And it, by the way, it's only part of science. It deals with fundamental phenomenon. And then, of course, it talks about validating the understanding of the fundamental phenomena you've identified. That's the scientific method's role. That's what it does. But if you look at engineering, engineering is a huge topic. It's much, much bigger than anything you'd call science, because it's not only humans, it's also all the life forms are practicing engineering. Engineering is actually a very, very big topic. That's one of the things we've now gotten more clear about. So there isn't actually just one method, I think, that would cover all engineering, except it's about creation, basically, and it's about for users, creation for users. That's basically what covers all of engineering, from life forms to humans. So I think then it in terms of its social impacts and so forth has to do with the users, what the users want it for. And there are a lot of creations which are not socially acceptable, probably. Okay, so that's going to be in that pool of what engineering does. So that'll mean it'll be essentially a practice-driven requirement rather than a foundational requirement, unless you want to rename engineering as in some way that makes it, acceptable to everybody, even the animals.
So talking about acceptability, I had a question maybe for all the panelists that capture some of the questions here, which is, we've been talking about how engineering is in service of humanity and, society. And it looks to me like a lot of the solutions that we are talking about may face a pushback at some time from humanity. So for example, if you look at autonomy, the first time an autonomous car, makes a big mistake, something big, some cybersecurity issue, and maybe it runs crazy and runs over even 10 people, that may shut down the industry, right? I mean, may be a big deal. Or the kind of thing that Professor Bashir was talking about, which is where you're developing some very invasive technology, and you can already see this in things like genetically resistance to genetically modified foods, which is a fairly benign use of technology, in my opinion, to modify foods. And there is already a big pushback, for example, from especially from Europe. So my question to kind of all of you, including energy, there's already with the new things that Biden is proposing, there's already a lot of pushback about using alternative energy or sustainable energy sources. So are we engineers short-sighted in that we're so focused on solutions to problems, or do we become sort of technically focused at problem solving and don't think about the fact that it has to become accepted, and we kind of think, well, they're going to accept it anyhow once it becomes commonplace? Is that an issue that maybe you can address from each of your perspectives?
I could take a stab at it if you want.
Please, yeah.
So I don't think you need to look at autonomous cars. I'm just stunned by 2020, the biggest thing that happened, maybe the Sputnik event of our generation, was the ramp up to producing 3 million doses of vaccines a day in about 5 months, and everything that came before that. And the fact that 30% of the US population doesn't trust this innovation, to me is it just strikes at the core of this issue. And I come back to, again, I remember the 3 fires, Dan, that you spoke about. I think communicating to the public, connecting engineering, what engineering is and what engineers do, and to engender the trust, I think is so important, so important. And it goes back to the earlier question we're asking about education. I think training students to be effective communicators, I think is important. I think training students to be responsible innovators, and this is the flip side, is also important. And I think, we talk about ethics a lot, and I quite honestly, I think nobody likes to be told what is ethical and what is not ethical. But on the other hand, everybody wants to be a productive member of our society, be a productive citizen, and contribute to humanity. And I think, couching that and making that an important part of engineering education, I think is vital. Although I do worry about this gulf between science and technology and society seems to be growing.
Yes.
In fact, science and technology has saved us, or is saving us in this pandemic. And for some reason, it seems to be going in opposite directions.
Yeah, if I may just add to that, I mean, I completely agree that at least, I mean, the lessons from COVID are so many. And one of them is that you can have a quantum leap in technology, but delivering that to people is an entirely different challenge. And I think that is true even in energy and climate. The reason it is political is because it affects people. And it affects everyone. And so for engineering solutions to be accepted, whether it's the market or by people, it is very important for engineers to be engaged in that dialogue. I don't think we can sit back on the sidelines and let someone explain why engineering is important. Engineers need to do that. And we need to understand what people need and want, and what are the issues that they're dealing with that may not be rational, frankly, and that's okay. But to be able to appreciate where people are today and help connect the dots between what engineering can do and how it would help them is very critical, because if we lose that narrative, we face a situation like Vijay was talking about, that trust is lost. And it's very, very important. If you're going to do the engineering to help people, the people need to understand what this is all about. And we need to be in direct contact with people, and so that we can explain and not let someone else do that and perhaps distort it along the way.
I think we can see the difficulty here by looking at the last administration we have of this country. This administration set out to poison our government in the minds of the people. And it started off by essentially attacking the media, the Washington Post, and so on, the Times, and repeatedly called them corrupt and against the government and against certain politicians over and over and over again for years. So the public has got entirely conditioned to not pay attention to anything the government says. Only trust me. I am the voice of truth and of what we need, and I am supporting you. Don't listen to the government. they got that message over and over and over and over and over. And that's what led us to the current situation where we have large fractions of the population that won't get vaccines. They won't trust it. And they even sponsored an attack on the Congress itself. Killed 5 people, as a matter of fact. I mean, it was not a small issue. And still they get protected by the people because the people don't believe the stories that they killed 5 people. They don't believe that actually there was trouble. So the country is totally divided on this problem, an issue I never thought in my lifetime I'd ever see, as a matter of fact. So when we talk about these issues right now, we're talking about the same thing is going to happen when the same kind of mindset people don't believe that what you're recommending is really necessary. It's basically going to profit somebody else, and this is all about some industry cabal to get money out of the people in some way or other. So it'll be something like that. You can just count on it at this point, because that's the way our country is currently thinking. So I think this to me is the big problem: is how we can actually get the people to back whatever kind of changes we want to implement. I think as Arun mentioned this, and others have talked about this, how we get the people to back what we want, what we believe needs to get done. Even trying to explain to people why you need to have a 2-degree maximum limit. Why is that going to be necessary? And all that sort of stuff. So this is one of the problems with democracy. You know, it's democracy.
But it's also happening in non-democratic countries. So the skepticism about engineering. So Rashid, I was wondering about whether when Dan mentioned vaccines, I heard that a lot of people believe that a microchip is being implanted with the vaccine. So when you're showing some of your microchips, I was thinking about that. So I'm just wondering, kind of going back to what Arun was saying, what is our I mean, we're not trained for it. We weren't trained as engineers to do this, or and I don't know how easy it is to. Vijay is saying, let's train the engineers. I don't know how easy it is to train them to traverse this very delicate path. And I've seen this in my own. I've been interviewed on some of these media, national newspapers and so on, and they always want a concise conclusion out of it, and but I'm always hedging, because we know in our research it's all about there is an 80% confidence that this is correct, and there is 20% probability. You hate to say this is what's going to do, and that's what they're looking for. Looks to me like that's at the origin of this trust issue.
Yeah, no, that's I think that's a very important discussion, and I mean I agree. I think from the curriculum perspective, we absolutely need to do more and do much better in integrating these concepts within our curriculum to not only produce the students who can solve the problem, but also understand that, like I think it's been said, that the problems are being solved for the sake of the planet, for the sake of humanity, for the sake of the ecosystem. So I think that sort of we do tend to, there's no question, we do tend to over engineer, and we tend to develop solutions without necessarily a problem in mind at times. And maybe enough of that is okay. Some of that is okay because you've got to try many things. But I really believe in this. No solution without a need idea, at least to push that. You need to understand what the real problem is. And then the fact that there is a human in the middle of that. So this usability, acceptance, trust, it is so important. I think we could do a lot more to integrate those concepts within our curriculum, within case studies, within design projects and other, to really have the students appreciate that exactly, I can invent the best solution, but it might not be adopted. So I think this, that's where I see the difference, marketing and communication. I mean, marketing is forward engineering of other people's perception about something. And I think you have to drive that forward. You have to work with those other disciplines and work with the other, domains across our campuses and figure out how to how do you integrate those elements or get our students enough exposure to them to really understand that the human factor is so critical, right, in all of this, and to how do you thread that needle? I mean, it's true, these things are complex, right? These decisions are complex. There is so many nuances to this. I also think that's where it is just really important, as mentioned by Professor Mote also. I mean, at the end of the day, you want the leaders to be able to understand and appreciate and put people in power, put people in positions of authority who understand that, right? I do think we need to figure out how we get to a point where we have a much higher level of scientific and scholarship and knowledge amongst our leaders of various organizations, entities at the government level, at the policy level, and other things that has eroded over the years, and we need to kind of push that back again. And science and engineering needs to come back. So, yeah.
Yeah, thank you. So maybe we can, in the few minutes, maybe 20 minutes, talk about some specific questions that have been coming. So there've been some questions on autonomy, Vijay, and thinking about would systems be safer if they were autonomous? Would the airplanes be safer eventually? And kind of going along, in fact, touching upon what Rashid just said, human is the center of this. So I'm wondering, will we reach singularity in this 21st century with a point where more and more autonomous systems will actually do better than human beings and perhaps be smarter than us? Will that be a point, what's often called a singularity, at a point where we start losing the initiative? And this is science fiction-y, but it's near possible. So how will that change technology? So
well, machines are already superhuman, right? So machines can out-calculate, out-compute. They can out sense. We're seeing that today. They can out-communicate. And if you think about Watson beating the Jeopardy world champion, remember Watson could hit the button in a fraction of in a nanosecond, while the human contestant had to spend about 80 milliseconds saying, okay, I know the answer, I'm going to hit the button. So the physical actions are also much faster. I don't know what you mean by the singularity, but by some definition, we're already past the singularity.
I think it's cognitive processes overall, right? So
I think I don't think it's well defined. Is what I would say.
I agree.
You could always define an axis and say, can you outdevelop humans? And probably.
Well, you showed a toddler, assembling the Lego blocks, and you said a robotic system still cannot do that, which is a combination of physical and mental dexterity. So those are so you can define it using tasks, perhaps.
No, but again, that's an unfair thing, because I would argue that if you set a challenge for a robot to assemble Lego blocks,
you can do it.
Yeah, I'll do it. So that was the point behind the grand challenge. DARPA said, well, can you drive a vehicle around? Well, certainly we can do that, but that's not the real world. And to say that that's your definition of a singularity might be dangerous. Yeah.
I mean, I think there's no question there are things today still obviously that can be done by the human brain, size of an apple and runs on sugar, versus what a supercomputer can do. I mean, there's clearly and just biochemical processes. I think there's a lot to be learned from on how that's done. I mean, how those processes are so I think unlocking the reverse engineering the brain is still, there's so much to be learned from that. That'll have implications on autonomy, right? I mean, I think also when you talk about computing, for example, what's happening now or what's potentially possible with quantum computing is gonna change everything in 50 years from now. I do believe that quantum, whether there's computing or whether there's communication, a lot of work needs to be done. And there's a question whether the goal itself is important there or the technologies that come along the way. But I think, there is some very exciting and some new paradigms. Hopefully if we can keep, there's no question, I agree with Arun, if you got to keep the temperature below 2 degrees to be able to see the the realization of all of these things, of quantum computing and of AI and in medicine and all these things, there's no question we got to keep the globe cooler. But there are some very new approaches and new ways of thinking around computing and intelligence that weren't around 30 years ago or 40 years ago to a level that it is there today.
Well, so it's I think Arun showed the graph of life expectancy doubling over the last century, which was to a large extent because of engineering, improvement of, for example, sanitation, and medical technology and so on, which we don't get credit for. Again, one more thing we can bitch about, but but I'm kind of wondering, going forward, we tend to it seems to be a trend over the last maybe 20 years where we say, look at nature. Nature is so much more efficient, so much more effective at doing something, because it's had billions of, maybe millions of years of evolution. Look at the bee, it can do all this, and look at the ants, they have such a social structure. So let's emulate that. Is that the right path to take? Because is that do we have an opportunity to kind of do a rapid evolution, and improve upon nature rather than kind of trying to be biomimetic? Is that a blind spot?
Well, I think that's what some of the ideas that are coming, from the bioengineering community, just to give that example, in trying to think beyond what we can replicate today, right? So developmental biology, learning from that to get to tissue engineering is understanding and mimicking. But then how do we use that to go to forward design of what the terminology that came out of an NSF center that was across MIT, Georgia Tech, and Illinois on forward design of multicellular systems, right? So can you truly design systems with cells that can do more than just what an organ would do today? So I think there's no question that this forward design, and if we can understand the design rules and the design principles of living systems or cellular, just call it cells of all types, whether it's animal cells, plant cells, insect cells. If you can learn the design rules, you can think about building systems that don't exist today, right? So that is going beyond what might be available today via just only by nature itself. So yeah, I think there are some really exciting and new opportunities there to be able to go beyond what's available today. So you got to go beyond biomimicking.
Mm-hmm. Yeah, please.
If I could just say a little bit on the energy side, we look at photosynthesis as, we survive because of photosynthesis. We would not be alive if it was not. But people forget that it is less than 1% efficient. And which is why biofuels are so expensive, because you need to gather all these plants from all over and concentrate them. Whereas fossil fuel, you just have to put a straw in the ground and it just pumps out under pressure. So on the other hand, what photosynthesis does is an amazing operation. Frankly, the design is so beautiful that it can take 4 photons at one shot and engineer how carbon needs to be split and fixed, CO2. And there's a lot to be learned from that. But at the same time, you got photovoltaics that are at 20% efficiency, 25% efficiency that is producing electricity. And so I think one has to look for perhaps inspiration from nature, but not always follow nature, because there is no internal combustion engine or a jet engine that nature has produced. But it has converted energy very efficiently, but at a much more distributed level. So I think there are some lessons from nature that you can take, but I don't think we need to follow nature, but take the stuff that we have, the materials and all, and put them together in creative ways to serve a function that people need. And I think that's where the engineering part comes in, that is not necessarily mimicry of nature.
I can add to that. I think there's also this other synergistic element. Sometimes you understand how something actually functions by building it.
It's different.
And I think engineered systems, well, we kind of know how we engineer them. And when you try to, you're inspired by nature, I think there's an interesting interplay that goes back. I think, Dan, your former colleague, Bob Full, is the one who convinced me of this. So robotics, once you start doing robotics, you understand lots of things about nature, which you otherwise wouldn't. So I think that's another element of it.
So there are some specific questions. Thank you for that. That's interesting. For Arun, they're asking about how do you deal with some technical issues? You just mentioned something about how the grids are designed for the essentially the fossil fuel energy, and it's we have to deal with major changes. Is that feasible? Will it take decades to do that? Are there surmountable problems?
Oh, they're absolutely surmountable problems. The grid was certainly not designed for fluctuating fluctuating supply. It was designed for fluctuating demand. And now we have fluctuating supply. And if you look at how the grid is balanced today, it is balanced in real time. There is no storage, very little. And the way it is balanced is when someone turns on a light somewhere, someone's generation has to ramp up. And the question is, how does the generation know that the light is turned on? And during Tesla and Edison's time, the only way to communicate between demand and supply is frequency. So we have 60 hertz, other parts of the world 50 hertz, et cetera, which is why AC grid is really important. But today we have other ways, much higher fidelity of knowledge, of communication, of what is happening in addition to the frequency. Frequency is still used today for balancing the grid. But let's say a generation goes down at a certain location. We know that what's going on. And thereby we can turn on a storage unit somewhere else or reduce the demand somewhere else. And we have much higher spatial fidelity than we had before. And I think the use of information technology to overlay as an infrastructure to manage the grid is going to be critically important in the future. And so I think it's very much a solvable problem. The challenge that is not trivial, and it's not an engineering issue. And we have scars on our back having served in the Department of Energy. Try building a transmission line from where the wind is, let's say South Dakota, all the way to Oregon or California. But that is not an engineering issue. That is aligning people's wishes in the local people's wishes, getting the federal, state, and other agencies to align the incentives to actually get the permitting and the licensing done for that to happen. And this is coming back to the engineering and people issue. I think it's very important for the engineering folks to understand that there are other factors that could be the bottlenecks. It need not be engineering. But to get the engineering solutions to help the people, you need to address them. And you need to understand and appreciate that.
So we need to keep coming back to the need to work with societal constraints. I think I'm just looking through the questions here. A lot of questions about education. So maybe I'll ask a very generic question. So it feels like we kind of partition these sort of 3 or 4 different areas here, but there's a lot of interplay between them. And to me, there seems to be sometimes even a conflict between them. So for example, an advancement in some AI technology may be at the expense of some solving energy problems. So it feels like all of these have to work in cohesion or some kind of concurrence or understanding of how other things are developing. So I'm just curious if any of you had any talks about, for example, and there's also beneficial. For example, AI has a role to play with implantable devices or whatever, and vice versa, or medicine and so on. So I'm just curious to know what you think about how the the interplay, and how we would manage this going forward, because we seem to be even today, very compartmentalized in our thinking. I know there's effort towards getting rid of it, but you see this all the time. So anybody jump in?
Yeah, no, I think from an educational pedagogical perspective, I mean, that's a really interesting question about, again, this comes between, I would say, kind of the depth versus breadth idea, but it's not just that, it's just that there's no question you need the depth. That's a given. But then how do you add the systems engineering thinking or the systems view of thinking, right? These interconnectivities, the fact that all these things are interconnected. I can't just design the most powerful processor, because I have to, of course, take into account the energy needs of that, and so on and so forth. So I think continuing to really try to integrate these elements so that at least the students we produce understand and they at least think of those constraints and criterias from a systems perspective. I think the more we can continue to push that, after the foundational sort of knowledge has been imparted, but then at the same time, even along the way, right, use those I'm a big fan of these case studies at the med school. I learned that when we were developing the med school curriculum, of actually creating cases. So, teaching the fundamentals via a case, that every topic is brought in from a perspective of a patient comes to the doctor's office, and that's what the patient is showing, the signs and symptoms. How do you measure it? How do you understand with the biology? So I really like those case studies sort of model. And the more we can come up with things like that in our engineering curriculum, I think we can it is possible to integrate these things without compromising depth at all, I believe. So I think that, and we still have many of our projects and things we do that the students do on a curricular basis tend to be still departmentally focused. I mean, broadly speaking, of course, at many of our places, it's already starting to cut across, but interdepartmental, cross-campus design projects, right? Cross-campus type activities. And it's really interesting because the registered student organizations on our campuses do that already. They have student organizations that have students from all over that come together around a mission, but our courses don't have that still in a way that we're just talking about. So I do think we do need to, I think our undergrad and curriculums do need that kind of a transformation that still hasn't happened, and it's time to do that.
Vijay?
Yeah, so if I can jump in, I think so linked to what you just said, Rashid, and again going back to this speech, Dan Mote's speech that I referred to. I think the bigger battle that we should fight as educators is attracting the best engineering talent, or the best talent to engineering. And so then if you step back and ask, well, what attracts students to engineering? It truly is about the grand challenges. So, I mean, I think Arun's talk, he talked about energy and climate as being the defining issue of the 21st century. I think if you poll students in any campus, engineering students, I think they'll agree with you on that. And so that's not neatly packaged into disciplinary areas. And so if you look at what we teach, and if there's one issue I would push back on how we currently do things, it's a very bottom-up process. I cannot understand, I mean, if I'm a mechanical engineer or electrical engineer, there's no way you get to energy and the environment and climate without taking a whole bunch of courses in physics, math, thermodynamics, and so on. And these courses are taught without any connection to the actual thing you want to get to. So I really like this idea of having case studies where you might teach things top down instead of bottom up. It is completely against our culture to do that, because we always say, student comes in, you send them off, take physics courses, chemistry courses, math courses, no connection to engineering. And we've agreed science and engineering are very different. So I think what unites all engineers are sort of these well-defined problems, societal problems, and that's what attracts engineers. But we do a very poor job of training our students. And I'm not talking about particular. I mean, this is just engineering education, and I think going back to the earlier question, an overhaul of the system, I think is important and timely. And perhaps, latching on to this case studies idea, and that's how you motivate students. That's how you get them started. That's how you expose them to different aspects of engineering and convince them that they should stay in engineering.
Yeah.
And I think bringing in this mission-driven idea, goal, it's really, the fact is that it will attract a broader set of students. It'll attract more women and more diverse students into our discipline, which is a big challenge that, this hasn't come up today yet, but this is, so I do think that making things that are more mission-driven, goal-driven, and figuring out how you integrate that in the curriculum so that those grand challenges get to students really early on from the freshman year, it's just gonna, I think, attract, we need to reflect the demographics of society. Engineering across the board is still not 50% women, right? Why isn't that? And I do think that adding that purpose-driven engineering is going to help with expanding diversity in the profession.
Yeah, we made a concerted effort, and I think over a period of 10 years, we are now double the national, I think, for women in engineering.
I could just go ahead. Sorry.
Go ahead, please. Yeah, I don't. Yeah.
No, I was going to say, we have just started. We launched a new school at Stanford, the first one in 73 years, on climate and sustainability. And we are going through the same debates and discussions internally, case studies, and exactly some of the things that Vijay talked about. And we basically said that we need to imagine a school of the 21st century, not be locked down on things that we did in the 20th century, because we are facing a 21st century problem. And so this is an experiment that is going on. And we've spent more than a year debating on campus. And I think that process of debate, and this is not just engineering, the law school, the economist, the business school, of course, the engineering school, the sciences, the medical school people, because public health is very important in this, all debating and discussing together. And this is in many ways, it has brought the campus together to actually get the school started. There's one more thing I would add, and we started an experiment. It's been going on for a few years and it's produced some great results, and that is education beyond the classroom. And what we have done in the energy field is create a fellowship program called the George Shultz Fellowship in Public Service. And we send our students to Sacramento, and we're going to send some in Washington, to be in the government, work together with the career staff people, not just the politicians. Politicians come and go, but the political appointees come and go, but the career staff people are there and really serve. And when they go to serve, they figure out, because the government is supposed to represent the people, and it does, what the people issues are. And they come back, first of all, with a very different view on education and engineering, et cetera. But what we're also finding is that Sacramento keeps calling us and said, can you please send those students back to Sacramento? And some of them got hired by the Utility Commission out here, some of them got hired by someone else, and they're now serving in the government. And it is an experiment that's turned out quite well. We are now going to start the Washington part, but I think it's an example of using the outside the classroom as a part of an education program.
I think we're kind of running up on time now, so maybe I'll give Dan the last word.
Well, first let me say, Arun, I agree 100% with everything you said in this last section, at least. This is the time to do exactly what you guys are doing about the 21st century education. Exactly right. Students today are ready to change. They want to change. They want to work. They want to work in the 21st century, and they want a 21st century education and opportunity. And I think all the things you're doing is just perfect, actually. Couldn't be better. And I congratulate the university for, well, what they see is probably a risk in some way of doing things differently, but it's actually not a risk. It's actually getting on the train, it's leading. It's not, it's leading. And I think that kind of leadership is what the 21st century needs, actually. And that'll take care of all the things we talked about today. Will fall into that category. So the students are ready to go. They are ready to change. They've already changed a lot just in 20 years. This issue about women and students, for example, and anyway, all these issues, the students don't have these problems. In fact, the students are really coming ready to be prepared to work and lead in the 21st century. That's what they want to do. So you got to look at it that way. They're not like old timers that have to be retreaded in some way. No. They don't have any treads to lose. They're ready to go. And I think they're coming with a much more forward-looking foundation. The only thing they're thinking about is getting a job. I want to get a job. I want to do something that has a future. I love this future, but can it be my future? That's what's on their mind. So I think in terms of education, that's what the universities have to instill in them, that you're going to the front of the line, basically, if you undertake these programs. So I believe that's one of the most important opportunities we talk about. Normally in our education systems, we're talking about training our students the way we used to do things in the past. We want them to have that foundation we all love and cherish so much, and so forth. I think that's a big mistake, actually. I think they can get the parts of that they want and still be looking forward at the time. And engaging them in things that are forward is what they like to do. That is exactly the reason why we have so many Grand Challenge Scholars programs nationally and internationally. That's all driven by the students, all driven by their interest to work in the future, work now, work on the problems. And in fact, most of the students actually, or at least half of them, essentially had to overcome their universities in order to create this program. Okay. I won't name this university, but eventually the students put together a team, and they've got a faculty member who's willing to talk to them, and they took it to the dean, and they forced the dean to go to the university to create the friggin' program. The students forced it, basically. So I don't worry about the students, actually. In fact, quite the contrary. I'm praying for the students that we give them a chance to come, and they have an opportunity now to make a big difference. This is a time for big differences, and it's a great time to be a student right now, because they'll be at the foundation of big change, and they'll be the big change.
Well, those are great words to close on, and I just wanted to say it's only natural that the students do this, because the future, it matters a lot more to them than to me, for example. I'm not going to be around to see it, so it's a very selfish interest, and it's the right one.
Once a fossil, always a fossil, right?
So this leads me to say that Engineer of 2020, the famous book, needs to be rewritten. It's high time one of you perhaps sits down and writes this Engineer of 2050 or something. I think it's due for a change. If you go back and read that book, which I did recently. So I'm sure we can discuss these topics, for our entire week. But we have to conclude it. We're a little past time. So you've given us a lot to think about. Again, the event was recorded. Telling all the attendees, you will receive the link to video by email. Please feel free to forward it. I hope we accomplished our main goal of emphasizing and bringing to light the enormous importance of engineering to society in the past and the future. I'm really grateful to this expert panel of professors Dan Mote, Vijay Kumar, Arun Majumdar, and Rashid Bashir for bringing us the benefit of their extensive experience and expertise, and for sharing the insight. Thanks to them for agreeing to come to this panel with late notice. I know you're very busy, and I really, really appreciate your changing your calendars around. I'm sure you have to do that in order to accommodate this 3 and a half hour slot. I also want to thank Beth Sharaga and Daryl Williams from the Franklin Institute for their continued support. Other members of the Civil and Mechanical Cluster of the Committee in the Science and Arts. Keith Argue for expertly curating the questions from the chat window. Dave Ahert for hosting and resolving technical issues with the webinar. Finally, the PowerPoint worked out. Finally, congratulations, Professor Dan Mote, for the Franklin Award. I hope today's symposium was a fitting tribute to your accomplishments and decades of contributions to the cause of engineering, many decades of contributions. Again, I'm Senior Nataraj of Villanova University. Really honored to be here, to be sharing the Zoom window with you people, and wish everybody a good day. Stay safe out there. Bye-bye.
Bye-bye, Michelle.
Congrats. Congrats, Dan.
Thank you.
Thank you all.
Thank you.
Thank you.
Thank you so much.
Thank you very much,
Everybody.
Michelle.
Congratulations, Dan.
Congratulations.